Hi everyone, thanks very much for coming to Toronto Data Workshop. Our guest today, Sayash Kapoor from Princeton, has co-written one of the books of the year, AI Snake Oil, What Artificial Intelligence Can Do, What It Can't, and How to Tell the Difference. And I think that it will be very highly rated in terms of end-of-year book lists. What makes the book so compelling is that the authors have deep expertise in AI. It's not the critique of someone who struggles to understand what an eigenvector is, or someone who cannot see both the potential of AI as well as acknowledging its limitations. And indeed, our guest today, Sayash Kapoor, is a computer science PhD candidate at Princeton. He's previously worked on AI in industry and academia, including both Facebook and Columbia, amongst other places. He's received a Best Paper Award at ACM Fact, an Impact Recognition Award at ACM CSCW, and was included in Time's inaugural list of the 100 most influential people in AI. So it's a great pleasure to welcome him to Toronto Data Workshop to talk about 5 surprises in evaluating AI agents. Thank you very much.
Absolutely. Yeah. Thank you so much, Rohan. And it's my pleasure to be here. So a lot of this talk is based on work that I've been doing over the last 6 months or so on evaluating AI agents. And I think before we even sort of begin, I want to go over what I really mean when I use the term AI agents. I think one of the reasons why the community as a whole has sort of started shifting away from just using language models as is and to compound AI systems or AI agents is that we've been seeing that, adding scaffolding on top of language models can allow these models to do tasks much better compared to using language models alone. So for example, on the slide here is one idea of what an agent might mean. You might have the ability to use tools such as code interpreters to execute code. You might have the ability to store things in short or long-term memory. You might have, at least in some sense, the capacity to plan. So there are modules that can sort of lay out what are the steps you need to take to solve a problem. And this is roughly what I mean when I use the term agent. So I won't go into like a very precise or specific definition, but it's basically a language model with additional scaffolding that allows it to solve tasks in the real world. And there is a lot of interest in AI agents from all quarters. So in the product world, we've seen multiple product launches that talk about agents. And if you are someone, for instance, who thinks that AI companies won't be able to scale language models all the way to AGI, then what we're going to see is more and more systems deployed on top of language models that can do real world tasks of interests. And that's probably what AI might look like in the future. So this is what led me to my interest in looking at and evaluating AI agents. We've also seen models like ChatGPT and Claude turn from simple input-output pairs to something that actually quite closely resembles agents. So for example, on the slide here is Claude 3.5 Sonnet that can now be used to develop basic JavaScript applications and run them on your browser. In addition, these models also have input and output filters. They can execute code. They can retrieve things online through web access and also connecting it to your documents. And they also have things like chain of thought reasoning, where the model thinks through something first or tries to sort of think through a given prompt step by step. So in this sense, agents are already widely used and successful. So that was the first thing that drew me to AI agents. The second is that on the flip side, there are also many very ambitious views of what agents can do in the real world. And there's a big gap between the hype around agents and the reality. So on the left, for instance, you can see a poster of the film Her, which is a vision of an agent that can autonomously execute tasks, have conversations, and so on. And on the right are examples of products that companies have built in the image of these visions and how poorly they've fared when the rubber hits the road. This includes things like Rabbits R1, where it is certainly plausible that this type of tool can order DoorDash. But instead of, if the tool goes wrong, even like 1 out of 10 times, and orders your food to your office address instead of your home address, that basically it makes for an unusable tool. And I think this is what makes AI agents really hard to get right, because we have many unsolved gaps for for things that language models technically might be capable of, but we cannot solve them reliably using these models. So over the next 30 or 35 minutes or so, I want to go over 5 things that I've found surprising in my work on AI agents, and hopefully they'll be useful in your research, and I would love to hear thoughts because a lot of this is work in progress. Okay, so the first surprising thing is that agents can, at least in theory, be infinitely expensive. They can cost an infinite amount of money to run because you can always call a language model one more time. And as a result of that, or as a corollary of that, we can sort of think about this one-dimensional leaderboard that is often used to talk about language model performance. For example, benchmarks like human eval for code generation or MMLU for knowledge understanding. They might not be the best fit for evaluating AI agents. And in particular, this is I think a quite strong claim because we have relied on leaderboards that measure the accuracy of these models for a long time. And these one-dimensional leaderboards are essentially how companies benchmark themselves, how they report their increases in model performance to investors, and so on. But this is different for agents because maximizing accuracy can lead to an unbounded cost, since reaching state of the art might just be a function of calling the underlying model many times. In fact, when we've looked at this trend empirically, what we found is that this trend can hold for up to millions of calls. So here's the AlphaFold paper that came out of Google in 2022. What they found is simply increasing the budget in terms of the number of times you call the model can lead to increases in accuracy. And this trend continues to hold for up to 1 million model calls. We have also seen similar results for other types of settings. So in this case, we found that for math benchmarks, we can increase the accuracy on the test set as we increase the number of generations, though the trend is not quite as clear as it is for the code models. And I think one of the most compelling pieces of evidence came out of Stanford earlier this year, which showed that we can keep increasing the accuracy on really challenging benchmarks like SWE-bench by simply increasing the number of times we call the model. So if all of this is true, and if we sort of appreciate the fact that we can simply increase accuracy by calling a language model more times, then that means that one-dimensional leaderboards are essentially useless in the sphere of AI agent evaluation, simply because you can keep calling the language model more times and increase accuracy. And that does not really tell us anything apart from how much money a developer is willing to spend on their evaluations. So in particular, one of the things that this sort of then leads to is instead of looking evaluations as a leaderboard, we need to take cost into the equation. We need to have two-dimensional leaderboards that emphasize not just the accuracy, but also the cost. And here's what an evaluation of one of the sort of leading benchmarks for code generation, human eval, might look like if we're doing this. So if we try to answer the question, what is the best agent on human eval, according to Papers with Code, which is this repository of leading benchmarks and models and agents, you might find these top 3 results. It's Agent Coder, a model called LDB, a model called Reflection, and a model called LATS, or Language Agent Tree Search. But if we sort of dig a little bit deeper and add cost to the equation, we have some surprising findings. So for instance, if we reproduce all of these agents with the publicly available code, but in addition to these state-of-the-art agents, we also evaluate simple baselines, such as just retrying a language model multiple times, what we find is that these simple baselines can actually perform about as well as these state-of-the-art agents, while costing about half as much. So on the graph here, warming is this method that we, or the agent that we call multiple times. And LDB is the language model debugger agent, which was at the top of the leaderboard. And what we find is that essentially there's a 0.1 difference in accuracy, but the warming agent costs less than half as much. So especially in domains where some sort of verification is possible, for example, in coding benchmarks, we might have verification in the form of unit tests. using this type of baseline that just retries the model multiple times is frankly, I think, essential for any leaderboard or any claim that a given agent is state of the art. And I want to stress that these Pareto curves, that is, frontiers that plot agents that are essentially optimal in this given set of agents, are essential to see these improvements. We cannot visualize these improvements on a one-dimensional leaderboard. More importantly, in many cases, academia might not care about the cost of running a given agent, especially because from the perspective of people writing a paper and because of the culture in the ML community, state-of-the-art results are emphasized above and beyond practical use. But for people who are using these models in the real world, for the downstream users, spending twice the cost for an agent that does just 0.1% better in terms of accuracy is absurd. And so that's why it's crucial to build in both these Pareto curves and evaluate against strong baselines that also account for cost. Okay, so this was the first sort of key insight I had in the talk. The second is that building on top of this, optimizing for cost is an underutilized design pattern in a lot of AI research. So I think a consequence of the one-dimensional leaderboards is that we have often optimized for accuracy alone. But once we start opening up the design space of how we can develop our agents, I think that leads to a mostly underexplored and underutilized design pattern. So in particular, I think we can jointly optimize both accuracy as well as cost. So for instance, we can use shorter prompts for language model calls that don't take as much in terms of the token cost or the dollar cost incurred. We can try to look for better few-shot examples that, again, have a smaller length or allow the model to sort of learn just from a couple of examples rather than relying on multiple ones. We can try to look for cheaper models that have the same results. And finally, we've also seen many AI developers rolling out things like prompt caching that allows you to cache often used prompts and then reuse them at a much lower cost. So how can we try to do something like this? I think one way to do something like this is to use software like DSPy. So DSPy is this excellent open source project out of Stanford that instead of relying on intuitions from the developers in how to develop the agent design, uses a small corpus of examples and then evaluates accuracy against this corpus to improve the agent design automatically. And so in particular, the way DSPy works is you specify a given accuracy metric, you specify a certain type of language model behavior, and then the language model is tuned. So the few-shot examples that are provided, the prompts that are given to the model are tuned to find prompts that are increasing the accuracy of the model on this given set of tasks. So far, what we've seen is the main focus of DSPy use has been for increasing the accuracy of models. We've seen some very cool results that simply increasing, simply like using more samples in terms of the few-shot examples or better prompts can lead to high accuracy. And we've seen this result over and over with DSPy. But what we instead did was we modified the default implementation to also account for cost in addition to accuracy. So in some sense, what we're doing is we are spending more on the fixed costs of finding better prompts, shorter prompts, better few-shot examples, and using this higher fixed cost to evaluate the space of AI agents, we are developing like an agent that actually incurs lower variable cost. And the reason this matters is if you're using an agent in production, it might be called hundreds of times, or thousands, or perhaps millions of times if it's a larger company. And so the variable costs very quickly exceed these fixed costs that we might incur. Okay, so we evaluated this system on a question answering benchmark called Hotpot QA. And we basically sort of looked at how the accuracy cost estimates go according to this Pareto curve. And once again, what we found was that jointly optimizing the accuracy and cost leads to a comparable model accuracy. So here you see the joint optimized model at about half the cost. And I think this is a picture that we'll continue to see over and over again. In this case, we used a very simple optimization algorithm. We basically just implemented some sort of discrete search over a number of possible few-shot examples and prompts, And I'm sure we can do a lot better than this. But I think what this shows is that this under focus on optimizing for cost has left open this vast design space of models that we might consider extremely useful, or agents that might be extremely useful in the real world, but have somehow not caught the attention of academia so far. So one of the counter arguments, or one of the arguments that I've heard people make when I present these results, is that language models are becoming too cheap to meter. That is, these costs are dropping exponentially. It is indeed true that there has been a 100x reduction from text DaVinci 003, which was OpenAI's model back in 2022, to GPT-4o Mini, which is perhaps a more capable model, but costs more than 100 times less. At the same time, there is some sort of like a trade-off for people who want to use these language models at scale. So if you're using these models billions of times, it might still be extremely costly. Like this still might be a dominating cost in running this application. And if we talk about academia, the impact of cost optimization can be even larger because right now, cost is a major barrier for research. So for example, in the paper that or the preprint where we presented these results, we spent around $10,000 in compute credits alone for the experiments to run our papers. Optimizing for cost also has implications for evaluating the safety of AI against real-world adversaries. So for example, we might consider cybersecurity attacks. Within this realm of cybersecurity attacks, different adversaries have different budgets. So for example, the recently released cybersecurity risk benchmark, Cybench, if we evaluate cost in addition to just the accuracy, it could tell us if, like a script kiddie or like someone who has extremely low resources can also carry out an attack successfully, or if it is only within reach for higher resource adversaries, or perhaps even just state-sponsored attackers. And finally, even if the cost of LLM calls might be extremely cheap, even in the medium term, we think that the total cost of running agents could still be very high. This is like, to illustrate this, I think one of these theories from economics can be extremely useful. So this is a theory known as Jevons paradox. Jevons was a 19th century economist who observed that as technological improvements increase the efficiency of using coal, this also increased the consumption of coal in a large number of industries. And so the total outcome was that we were actually using more coal compared to less, even though the cost of using this coal was going down. We've also seen this play out in many other domains. So for example, in case studies of automation, when ATMs were first introduced, lots of people thought that this would make bank tellers and bank jobs obsolete. But instead of that, they actually led to an increase in the number of bank jobs because it was so much cheaper to open a new branch. And a similar trend could hold for AI models as well. So as these models get cheaper, we might start calling the same model many more times in order to solve the same exact task. And we might start using these models for many more applications. Okay, so this was the second part of my talk. The third part focuses on shortcomings in agent evaluations. So even if we set aside the fact that overall compute is unbounded for AI agents, there are many other factors that we've seen go wrong when it comes to AI agent evaluations compared to model evaluations. So for example, one of the claims that we've seen companies make repeatedly is when it comes to declaring how well their models work compared to other ones. So here we have seen some use of Pareto curves. For example, this is a figure that was introduced by Mistral when it launched its new mixture of experts model of series of models. What it did then is, instead of using cost in terms of the dollar costs as the x-axis, it instead focused on the number of active parameters in the model. And this has led to, or this is the key misleading claim in this slide. So basically, if we look at just the number of active parameters as a proxy for cost, we would come away thinking that Mistral's 8x7B model is more efficient compared to Llama 2's 13B model. But actually, because of the costs of running mixture of experts model are higher because of the additional memory use, the cost of running a Mistral 8x7B model is almost twice the cost of running a Llama 2 13B model. According to this graph, they cost the same because instead of using the actual dollar amounts as the x-axis, developers have started using proxies, like the amount of compute used or the number of active parameters. And while all of these metrics might be interesting from a scientific perspective, researchers really care about compute control evaluations to see if the training methods are doing better. But for downstream users, the main construct of interest is just the cost. So I think this is just one of many differences in language model evaluations and agent evaluations. You might have other differences as well. For example, for language models, evaluation consists of simple inputs and outputs that are all strings. But for agents, it might involve taking an action in the real world. For example, a coding agent could be asked to take some piece of code and execute it on a virtual machine, which is very different from just using a language model to evaluate inputs and outputs. We've already discussed the cost differences at length. And a final difference that I want to emphasize is that language models, in some sense, are a lot more general compared to agents, because we also have seen that task-specific agents, for example, the SWE agent that was built specifically for solving software engineering tasks on SWE bench, can be purpose-built for a specific type of task. So all of this is to say that I think we need to fundamentally reevaluate our approach when it comes to agent benchmarks. And that's also because agent benchmarks are already being used for extremely consequential decisions. So we've seen them being used to make funding decisions. For example, this model called Genie received millions of dollars in funding based on how well it scored on agent benchmarks. Similarly, we've seen Cognition AI, which is the company that develops the Devin software agent. Their valuation increased from $350 million to $2 billion US in a matter of weeks after they released their results on SWE-bench, which is an agent benchmark. But at the same time, existing benchmarks also have many, many shortcomings. One of the shortcomings is that these benchmarks are often not useful in the real world, so they don't measure something that's actually of relevance in the real world. Another is that oftentimes we don't really have basic sort of ML hygiene. So one of the things that is textbook ML knowledge is we need to have a held out test set when we're evaluating models or agents for real world performance. But what we found in a survey of agent benchmarks, and this slide is very small, but all of the red crosses here essentially show agent benchmarks that have no held out test sets. So we are basically training or developing these agents on the same data set that we're using to evaluate them on. And I think this is a key reason why a lot of the agent results that we see today cannot really be trusted in terms of real world performance or real world generalizability. Now, we've also had similar concerns with language model evaluations. And in this case, we've seen frameworks like Stanford's Helm, which is the holistic evaluation for language models framework, as well as Hugging Face's OpenLLM leaderboard that sort of standardize these evaluations. These are maintained by third parties that evaluate models with a standardized evaluation harness and provide full transparency into every single model call that is made during this evaluation. And I think something like this is missing for agent evaluation. So this is one of the things that we are working on right now, which is basically we're calling it HAL, a holistic agent leaderboard, which is specifically designed to address all of the issues we discussed with agent evaluations. So it is run by a third party. It is ourselves and a coalition of other researchers. It is standardized, so every single agent is evaluated in the same way, and it is cost controlled. So on the bottom left, you can see in a very small font, this Pareto curve that is automatically generated for every single agent evaluation. Okay, this brings me to my fourth point, which is that task-specific agents drastically outperform more general agents. And here's what I mean by that. I think in the past few months, we've seen many claims that agents can be used, like the same agent can be used for solving a number of different kinds of tasks. And I think this has been a trend. If we look back in machine learning, this has always been a trend. They're always aiming for more generality. But what we found so far is that these agents have robustness issues, they have reliability issues. So I want to discuss one specific case study of a benchmark that we created to test this phenomenon. So one of the motivations for building this benchmark was the difference between claims about AI being used for scientific research and the reality. So for example, a company called Sakana AI introduced the AI research agent, or I think they called it the AI scientist, which they claimed could fully automate all parts of science. They even put out a few research papers that were claimed to be authored by this agent. And so we have these claims, very strong claims by companies on the one hand. And on the other hand, we also have what is essentially a reproducibility crisis already going on in a lot of scientific fields. So leave aside AI agents. Even humans can't seem to be able to reproduce papers, even when the data and code are available. So this is a brief survey of all of the different fields where this type of reproducibility error has been found. We call this computational reproducibility. And I think including this has affected fields including like machine learning and finance, political science, geosciences, computer systems, and so on. So motivated by both the tall claims that the companies are making, as well as the reality that we are already unable to implement and reproduce many papers, we built a benchmark that we call Core Bench. And the key thing that we want to test with this benchmark is whether AI can automate computational reproducibility. In particular, an AI agent is given a task that is derived from a specific scientific paper. For instance, let's say a psychology paper that reports the correlation between a feature and an outcome, and the code and data that is accompanying this paper. And the agent is tasked with recreating or reproducing the results using this code and data so that we can verify if the original paper is computationally reproducible. So we do this thing for about 90 different papers from computer science, medical sciences, and social sciences, and for 2 different languages, Python and R. And we have 3 levels of the benchmark. So for each paper, we have an easy, medium, and hard level. Now, what we found was somewhat astonishing, which is that in stark contrast to what you might expect, given the claims that models like GPT-4 can already automate a significant chunk of scientific research, GPT-4 got about less than 10% on this benchmark. GPT-4 mini even less. So this is in terms of the general agents that people have claimed. In particular, we use the AutoGPT framework. That is one such general agent that is used for solving tasks across domains. In addition to this, we also created a task-specific modification to AutoGPT, which sort of created some guardrails for checking if the model outputs were correct and so on. And this drastically outperformed the domain general agent. So I think one of the key results that this basically shows, or one key thing to take away from this, is that task-specific guardrails can be really important in having agents perform well on specific tasks. We are still a long way to go in terms of how well these agents can autonomously execute tasks in a wide range of domains. And so having these specific guardrails can be very helpful. Another thing that we have a long way to go on, though, is in solving computational reproducibility itself. So even if we leave aside the fact that AI cannot automate all of science, and even if we look at this very small subset of scientific research, which is just reproducing past results, essentially like a key component of any empirical field where you're trying to compare against baselines from past research, we see that only in about a fifth of the cases can AI agents with task-specific modifications solve these results. And I think one of the things that we try to do with this benchmark is to keep these tasks as close to the real world as possible. So improvements on this benchmark would translate to improvements on the real world tasks of interest, which is reproducing papers automatically. It also sort of could save time if we were to get to agents that do well on this benchmark. It could save time in terms of the millions of researcher hours spent on reproducing papers. And I think we would also start then thinking of institutional changes. For instance, things like journals using these agents to verify the reproducibility of submitted papers. One last thing I want to stress from this section is the capability reliability gap. So what this means is if language models were reliable enough at solving tasks that they're already capable of, then I think the effects would be already transformative. And essentially what we're doing with these task-specific modifications is to improve the reliability of these models, such as by building simple guardrails. So for example, when we built Core Agent, the guardrail that was most effective was basically just checking if the paper was outputting the JSON in the correct format. That was alone enough to increase the performance by several points of accuracy. And compared to doing like the somewhat more challenging tasks of actually reproducing the paper, it was at this step that the generalist AutoGPT agent failed several times. Okay, this brings me to my last and final point, which is based on ongoing work with Benedict Strobel and Arvind Narayanan, which is a somewhat tall claim that there is no free lunch in inference scaling. So some of you may have heard the term inference scaling that is now being described as one of the key things people are doing to improve language model performance. Essentially, it boils down to what we discussed earlier on, which is calling language models many times. But there are many versions of inference scaling. So here's a schematic diagram. In one of these methods, we might think about using ensembling. So a generator, that's a language model, generates multiple solution candidates. We ensemble them in some way, such as by taking a majority vote, and we output that result. We could also think of things like re-ranking. So you have a ranker model that looks at the various output solution candidates generated by the generator and then ranks them, and you pick the model that has the highest ranking by the ranker model. And finally, we could think about inference scaling by repeated sampling in the presence of a verifier. So in problems such as coding, a verifier could just be something like a unit test. So you look at the proposed solution by a generator, and you run those unit tests. And if the unit tests fail, you reject it, send it back to the generator, and you keep doing this until something passes and you accept that solution. And I think this third category is where we have seen a lot of interest and a lot of promise in the last few months. So for example, I'm referring to this paper by Brown et al. Again, which showed that as we keep increasing the number of samples, the accuracy, or like the probability that at least one of these samples would output a correct answer, keeps going up. And this has some smooth sort of scaling properties. It goes up in some predictable ways. Now, it's clearly not enough to keep generating these samples. What you also need in this third type of system is a verifier. And unfortunately, what we found is that verifiers can be very weak in practice. So for example, the extremely popular human eval and MBPP, which is, I think, mostly basic Python problems. These are two benchmarks that are used across the board by developers, but they're known to have false positives in the unit tests that are accompanying them. And similarly, if we consider the verifiers in some point in the future could be automatically generated using language models, they could have false positives and also false negatives if the unit tests are incorrect. So a natural experiment, or like an interesting thing that sort of the ML community released, is updated versions of both of these benchmarks, which are Human Eval Plus and MBPP Plus. What these benchmarks do is they have a large number of additional unit tests that avoid the false positives, or that are aimed to avoid the false positives that could arise with the original benchmarks, Human Eval and MBPP. And this essentially serves as the test bed for our experiment. So what we then did is we saw what happens if conditioned on the original solutions generated by a model passing the earlier unit tests in Human Eval and MBPP. What happens if we look at the accuracy of these models on Human Eval Plus and MBPP Plus? So for the purpose of this, for the rest of this presentation, we can assume that the accuracy of these models, which is the true accuracy, is essentially given by Human Eval Plus. And then we have a certain verifier, which is the unit tests in the original Human Eval and MBPP algorithms. So here's what happens when we plot the correct accuracy conditional on the unit tests and the single sample accuracy on the total number of unit tests in Human Eval Plus and MBPP Plus. What we find is that weaker models are far more likely to create false positives. That is, false positives basically mean solutions that pass the original unit tests, but not the expanded set of tests. And what this also means is that in the presence of this type of imperfect verifier, there is a natural ceiling to how well these models can work. So in particular, if you look at this horizontal line here, this represents the pass-it-one accuracy of GPT-4o, which is a strong model in this case. If the conditional probability of a weak model, even conditioned on passing the unit tests, is lower than a strong model, in this case, GPT-4o's accuracy, without having this verifier, then there is essentially no amount of inference scaling that can lead to this accuracy gap being closed. So in other words, the promise that we saw of inference scaling was predicated on there being a verifier that won't allow these false positive solutions to pass. But in the presence of these false positive solutions, all bets are off. And for example, all of the models in this region here, which are below the GPT-4o pass-it-one accuracy, cannot outperform GPT-4o even with an infinite amount of compute. This type of result becomes even stronger if we consider that in the real world, false positives have a negative cost or a penalty associated with them. So for example, the usual inference scaling laws that we see keep going up over time. But if we introduce a penalty for false positives, that is solutions that match the or pass the unit tests, but nevertheless are incorrect, that changes these inference curves significantly. In fact, this is what they look like. So on the top here, the green line is inference scaling without any penalty. And then as we go down, we keep changing the ratio between the penalty for incorrect answers and the reward for correct answers. And what we find is that introducing a reward basically just bends these inference curves downward. And so, for instance, for Llama 3.1, if the penalty ratio is 1, the optimal value of k, like the optimal number of times you could sample, is between 10 and 100. But the crucial point is it's finite. So even if we have zero computational cost, even if resampling from a model is free, the optimal number of times you should resample becomes finite. And in fact, as we increase this penalty, as the cost of false positives goes up, this optimal number of samples keeps decreasing to the point where for a ratio of 8, and this is for human eval, the number of optimal attempts is just 1. Okay, so this is sort of this was the last sort of key finding or surprising thing about inference scaling, is that while often we hear claims about there being a free lunch from inference scaling, that we can keep resampling in many times, including at the beginning of this presentation. Unfortunately, in the real world settings where we have imperfect verifiers, there are certain limits to inference scaling and how well it can work. So this brings me to the end of the talk, and I'm very happy to take questions.
Thank you very much, Sayash. That was an incredible talk. Are there any questions from folks? If you have a question, feel free to raise your hand, or if you don't want to ask your question yourself, you can add it in the chat, and then I can read it out for you. But maybe we could start with totally not a robot. Do you want to just elaborate on yours if you'd like, or I can do it for you if you'd like? Mic is broken. Okay, so the question was, so it was with regard to task-specific agents, and the question from the chat is going into detail about verification. And real world examples or considerations for creating a model that does that. The example is providing the AI providing unit tests.
I see. So is the question whether there are real world examples of tools that rely on AI generated unit tests in order to see if the model works well?
Yes. Yeah. that from the chat.
Cool.
Yes,
Yeah.
exactly.
Yeah, there are certainly like several such attempts. So I think in the research literature, we've seen papers that try to do this for program synthesis, for math problems, and for coding. I think that's because these are the three places where we have clear definable unit tests. So for coding, we have like literally just the unit tests. For math, we can have automatically generated word problems, and for program synthesis as well. But I think in terms of real world applications, I'm not yet sure if I've seen examples of people trying out unit tests. I do know that for OpenAI's O1 series of models, they did something similar but distinct. So it was similar in the sense that they are sort of using these different sort of trajectories of model outputs, and then the agent is picking one of those. But it's different because this is not happening at inference time necessarily. This is trained into the model when the model is during pre-training, or like there's a separate step that is modifying this model behavior. It's not just about inference time improvements.
Nibras?
Hi, it's a nice presentation, Sash. Thank you for sharing this. I have one question. Would you please elaborate the term of the model call?
Yeah, sure. So basically a model call is when you type in like a certain input, or you have like a specific query that you're making for the model, and then you get an output from the model. So essentially for the longest time, what we saw was you basically just evaluate these models by asking a question once and getting an answer once. So for example, if you wanted to evaluate how well ChatGPT does on solving legal questions, then you might ask a legal question and look at its response. But I think with agents, the key distinction is that you don't just think of these as one single model generating one string. You can think of them as like an entire system around a model. So you might call the model, you might have like 100 different responses from the model. And then you have some mechanism of choosing between these 100 responses. For example, you might have ensembling. So from all of the model calls, from all of the solution candidates, you are sort of ranking them in some order, or like merging them in some order, or perhaps even using a verifier to keep calling the model again, to keep generating solution candidates.
Paula from the chat asks if you have considered or would consider in the future environmental costs or impacts as dimensions in addition to financial costs.
Yeah, that's a great point. I think in some sense, financial cost is roughly similar to environmental costs, especially as we're seeing all of these models being run at near cost because of the competitive dynamics of the scene right now. That said, I do think like incorporating environmental costs is not definitely or definitively going to work in terms of the actual impact of these models on the environment. So in particular, I want to remind us of the Jevons paradox, which is literally like the example that the economists saw was coal efficiency improving, and that leading to much more coal being used rather than less. And so if the concern is about the total impact on the environment, I'm not sure if such quantification is likely to lead to like a reduced reliance on AI or LLMs overall. But yes, I do think in terms of improving like a specific company's practices, that could be very useful.
If anyone has any questions, feel free to raise your hand or to add them into the chat and I can read them out. Maybe while folks are thinking, Sash, do you see this as a classic academia industry divide? So for instance, Apple just released its AI models. They need to work on my iPhone. So they're going to be very constrained in terms of their compute and their time and their costs. And maybe we're just missing things in academia. Do you see an aspect of that, or do you see that this is a real problem faced in both industry and academia?
Yeah, that's a great question. So I do think industry is more incentivized to work on cost optimization, but I think in some sense, like I think it is a blind spot for academics as well. And so in part because of the culture of like a one-dimensional leaderboard, I think everything else is deprioritized compared to getting state-of-the-art results or state-of-the-art accuracy. In fact, I've heard multiple reports from like grad students and early career people who are sort of incentivized to game the leaderboard in order to get their work published, because without it, you don't really have good odds at the top conferences. And so I think part of it is definitely this culture within academia. That said, I do think academics have a role to play in developing a lot of the innovations needed to sort of get to that point. So one of the things that I think academics can do very well is working on cost optimization frameworks. I think they would be useful beyond academia for industry as well, but they do also have academic merit. And in general, I do think we need to sort of change the incentives a little bit more to value all of these different types of contributions rather than just like a single-minded focus on one-dimensional accuracy.
James from the chat says, can you tell me a little bit more about the trade-offs between prompt caching and just calling the model? What is the upper limit or usefulness to prompt caching, please?
Yeah, that's a great question. So I think prompt caching basically just stores a given text that you input into the model. And then if you're calling the model with the same text over and over again, then the stored text costs about half as much as calling a model again would cost. And so I think in some sense, there are no real trade-offs. The only trade-off is sometimes you have to pay providers some money for storing this text in the first place. So for example, let's say using OpenAI's GPT-4 series of models, and you want to add prompt caching to it. If you're like an ML company that uses the same prompt over and over again, then it might make sense for you to store this, I don't know, like 10,000 token prompt. And then when you call this model, you're paying half the cost for it. But the flip side is you may have to pay something like $1 per hour per 10,000 tokens to the company in order to store that prompt for you. So I think you're basically just trading off the memory cost of storing this prompt with the reduced computational cost that you have to pay the company for calling the model. So I think in some sense, if you're calling a model like millions of times, it's basically a no-brainer. There's very little in terms of trade-offs.
If there are any questions, feel free to raise your hand, or I can or add them to the chat. So in martial arts and things, there's weight class divisions. So you can be the heavyweight champion of the world, middleweight champion of the world, and then there's by gender. At the moment, we seem to just be going for, the best boxer or whatever in the LLM space. Could you imagine a world in which we have these different classes and of evaluation?
Yes, absolutely. And I think that's what companies like Mistral were trying to do with the number of parameters for these model calls. So I think in some sense, even in the AI development world, we've seen this type of like class division based on the number of parameters or the compute used to train the model. That said, I think what is far more like useful or general is just getting rid of this proxy variable and just focusing on the dollar costs. In particular, because if you have a small model, you can sort of still call this model multiple times. You can try to sort of, increase accuracy just by resampling. And that could still incur similar costs as a larger model. And so instead of having like a weight class defined by the properties of the model, I think we should think about weight classes, if you will, defined by properties of the agent in terms of how much it costs. And so in some sense, like, yes, that is exactly our proposal, is to have these types of Pareto curves that have both cost on the x-axis in addition to accuracy.
From the chat, Totally Not a Robot says, if I wanted, I think you're doing great work. If I wanted to learn more about your research, where should I look?
Thank you. Yeah, I think our website, aisnakeoil.com, has a lot of our work on it, including our research and also things about the book. So I think that would be the right place to start.
Could you talk? I'm noticing a few questions from PhD students that we've asked. Could you talk a little bit about your approach to research and how did you pick which questions you're going to work on? How do you approach these sorts of things?
Yeah, that's a great question. So for context, I work at the Center for Information Technology Policy. I'm a computer science graduate student, but a lot of my work is related to how should we govern AI systems and what role policymakers should or should not play in that process. And so in some sense, like I see my interests being on technical questions that can inform questions related to governance. And so, for example, some of my past work has looked at the impact of open foundation models, that is, models whose weights are released openly, what risks they pose, how we should think about regulating them, and so on. And I like to think of my work as providing the technical basis for evidence-based policymaking. I think it is very similar for AI agents. We are not yet in that position, but I think in the next year or two, we'll start to see interest from policymakers in the governance of AI agents that are acting in the real world, much like we saw with automated decision-making systems in the last 5 to 10 years. And I think when we do reach that stage, we need to be in the right position to understand the impact of these systems on the world. We need to understand how well they work, what the risks are. And I think I see a lot of this as sort of basically laying the ground for that conversation to come. So in a nutshell, basically looking at interesting technical questions that can inform evidence-based policy.
And I'm not seeing any other questions, but maybe just want to sort of just sum up. What sort of things are you most excited about working on in the next year or two?
Yeah, I think the governance of AI agents is definitely one, but then also thinking about how far we can take the current paradigms and what the limits are. So I think the first part of the talk was about the first question, which is how far current paradigms will take us. There we see some hope for inference scaling, some hope for scaffolding, some hope for general purpose, task-specific agents compared to general purpose ones. And I think all of these will continue to be important questions as we see the next wave of models. And then on the flip side, I think it's also important to be grounded in what the limitations might be. So I think some of this upcoming work that I talked about, such as the limits to inference scaling, is focused on looking at how far, or if there are like inherent limits to how well these models can do when used in the real world.
Sayash Kapoor, thank you very much for joining us. An absolutely fantastic talk, based on fantastic research, and I really appreciate your time.
Thank you so much. It was a pleasure.
Thank you, everyone. Have a nice rest of the day.